molecular orbital theory about H2 plus molecule ion. And what we found is that the linear combination of atomic orbitals of two 1s orbital of two hydrogen atoms gives you two molecular orbitals, bonding molecular orbital and anti-bonding molecular orbital. And the detailed calculations of the wave functions and everything we talked about. Now, how to go beyond H2 plus molecule ion? So I thought I should give you some introduction to a qualitative part of the diatomic molecules, which is already with you, which you have done in your undergraduate level also. But just to recap everything, if you look at that molecular orbital theory of diatomic molecules, then we have seen in H2 plus molecule also, in other diatomic molecules also, the molecular orbitals are found by involving all the wave functions of atoms involved in the molecule. If it is diatomic molecule, you involve two different orbitals, 1s and 1s for H2 molecule. Okay. Then again for higher diatomic molecules like N2 and O2 you go, then 2s and 2s can combine, 2p and 2p can combine. How do they combine? This we are going to talk about in the today's lecture. So molecular orbital involves all the atomic orbitals simultaneously, while in hybridization only the central atom orbitals are involved. So that differentiation you must make. Okay. And then molecular orbitals are formed by linear combination of atomic orbitals that we have done already. Okay. And hybridization is the combination of atomic orbitals of central atom only. That's the fundamental difference between the two. When the two combine, there is a constructive and destructive interference. This already you are aware of, that 1s and 1s interaction takes place, and in between the internuclear space, this is one nucleus, this is one nucleus 1, this is nucleus 2, and in between the nucleus the electron density increases when there is a positive interference, constructive interference, and the molecular orbital which you obtain could be written as psi 1, phi 1 plus phi 2. Okay. It's exactly same as we did in H2 plus molecule ion. So we are talking about H2 molecule. So here also we have, the only difference is that here also you will get two molecular orbitals, bonding and anti-bonding molecular orbitals, but the electron is 2 here. In the case of H2 plus molecule, the electron was 1. Okay, and a destructive interference will take place, and this will be the node will appear in between the two nucleus. When this phi 1 minus phi 2 you do, and out of phase interaction takes place, destructive interference takes place, then you get a different molecular orbital called anti-bonding molecular orbitals. And if you look at the charge density, then what happens, that the square of the wave function gives you the probability or the charge density or electron density. Okay, probability density plot you get from square of the wave function. So if you square this function, then you get an additional terms of 2 phi 1 phi 2 with a positive sign. So electron density increases in constructive interference, in phase interaction, and on out of phase interactions, you get the same amount 2 phi 1 phi 2 but with a negative sign. So the electron density decreases. It's very fundamental thing which you have already done. And the molecular orbital which you obtain from this interaction, out of phase interaction for destructive interference, is called anti-bonding molecular orbital. All anti-bonding molecular orbitals are written as a star sign, given a star sign for anti-bonding molecular orbital. Okay. Now, if you look at the energy level diagram, then this is the energy level diagram for bonding molecular orbital. You have interaction take place, and you have no nodes in between the nucleus. But for anti-bonding molecular orbital, you have a node. You have a node, and this is the energy level diagram. That the lower energy orbital is called bonding molecular orbital. So no star sign here, but higher energy orbital is called sigma star because it has one node, and it's formed by destructive interference. Okay, so this is the energy level diagram, and if you look at the energy gap, then energy gap between the two will be, if the energy gap between the atomic orbital and the bonding molecular orbital is delta E, then energy gap between bonding and anti-bonding molecular orbital is 2 delta E. Okay, so that's also something which you have already done in your earlier courses. Okay, then if the atoms don't have the same energy, here we were talking about H2 molecules, so both will contribute both will have a 1s atomic orbital and both will have equal energy. But if it is not so, if the orbitals are different energy, then what will happen? Then also the interaction will be similar, but one of the orbital will have lower energy, A orbital has lower energy, and B orbital has higher energy. B atom has higher energy. Okay, for a hypothetical molecule AB, and what you see is that the bonding molecular orbital have major contribution from A, and anti-bonding molecular orbital will have major contribution from B. The color tells you the thing. Okay, it means that when you talk about the linear combination of atomic orbitals psi LCAO, and you say C1 phi A and C2 phi B, and since it is linear combination, so plus minus, then this C1 value and C2 value will be different in the two cases. In case of bonding molecular orbital, it will be something else. In case of anti-bonding molecular, it will be something else. If the A contributes more to the bonding molecular orbital, then for bonding molecular orbital, C1 value will be higher and C2 value will be lower. In case of anti-bonding molecular orbital, B contributes more, so C2 will be more and C1 will be lower. Let's see what is it. The bonding molecular can be the same thing which is written here, that Ca alpha sigma greater than Cb sigma for bonding molecular orbital. Okay. And look at this point. The linear combination of atomic orbital is same thing. Ca sigma is greater than Cb for bonding molecular orbital, and for anti-bonding orbital Cb sigma star is greater than Ca sigma star. Sigma I am saying because the combination is along the molecular axis, and we have talked about hydrogen atom, so it doesn't matter either along x-axis or y-axis or z-axis. Soon we will see how does the assignment of the molecular axis changes the combination of atomic orbital to give you molecular orbital. Okay. So if this is your linear combination of atomic orbital, then for n is equal to 1 psi 1, Ca1 is 0.8 and Cb1 is 0.2. See, the contribution from A is higher, 80% contribution from the A, 20% contribution from the B. In case of psi 2, 80% contribution is from the B and 20% contribution is from the A. So whenever there is a difference in the energy levels of the combining atomic orbital, this happens that one orbital contributes more than the other, and or bonding becomes more closer to the lower lying atomic orbitals. Anti-bonding becomes more closer to the higher energy atomic orbitals. Okay. So this is, say for example, if you have a case of HF molecule, then this thing will arise, because H1s orbital of hydrogen and F orbital P orbital of F molecule, fluorine molecule, will have different energy, and in that case the contribution will be different in case of different molecular orbitals. So what kind of interactions is possible? Okay, we said that SS overlap is possible, PZ overlap, and now I have said let the molecular axis is Z axis. We suppose that the molecule lies along the Z axis, and if it molecule lies along the Z axis, then PZ and PZ combination and S and S combination are the combination which will be overlapped along the molecular axis, and this will give you a sigma molecular orbital. But px and py overlap will be perpendicular to the molecular axis, and this will give you a pi molecular orbital. So this is the fundamental difference. Okay. So again, it's a positive combination, and at the bottom it's a negative combination. So in the top one, these will give you positive combination will be constructive interference, will give you bonding molecular orbital, and negative combination will be destructive interference and will give you anti-bonding molecular orbital. Okay. So some orbit, but always there are cases in which orbitals overlap is not possible also, because you look at this point where an s orbital is combining with a px orbital. And what does it mean? It means that this area which is overlapping on the positive x-axis and this area which is overlapping in the negative x-axis will cancel each other, and there will be zero overlap. So this kind of combination is not possible. Again, you see it's a dx square y square or dxy, and then you have py orbital, so it is dxy and py orbital. So this also will not overlap, because the overlap which is taking place in the positive side and the overlap which is taking place on the negative side will cancel each other. So all kinds of overlap is not possible. You will have to see that the atomic orbitals which is combining to give you molecular orbitals must be capable of overlapping. Then only they will overlap. They will show the two kinds of constructive and destructive interference and will give you bonding and anti-bonding molecular orbital. Okay. But if your molecular axis is x-axis, z-axis, and the s orbital is overlapping, then s and pz can overlap, because I will show you. Okay, this one. S and pz can overlap. Look at this one. S and pz can overlap. SS can overlap. PZ can overlap if the molecular axis is z axis, and all these axes will be along the z axis. All these overlap is along the z axis, which is the molecular axis. So they will give you a sigma molecular orbital. In contrast to this, px can overlap. Py can overlap. This is a positive overlap. This is a negative overlap. Okay. This is a positive combination. This is a negative combination. Okay. This one is a positive combination. This one is a negative combination. So this will give you a bonding molecular orbital. This will give you anti-bonding molecular orbital, and this the same picture will be with the py also. So px and py overlap is possible, but now the overlap is not along the molecular axis. It is perpendicular to the molecular axis. So it will give you a pi molecular orbital. Okay. Same way, and the result will be, if you have a pi molecular orbital, we will show you the delta overlap will have two nodal planes passes through the bond axis. Okay. And anti-bonding is given a star sign that I told you. Delta bonds we will not talk about much. Okay. So if the leveling of these molecular orbitals is also done in terms of symmetry as G-rayed and un-G-rayed. Okay. Whether the molecule is centrosymmetric or not, whether the molecular orbital is centrosymmetric or not. If you have to find out, then you look at the molecular orbital and find out the center of the molecule. And from the center of the molecule, you move along positive x, positive y, positive z, and negative z. In both the directions you move. And if you get the same sign of the wave functions on both the sides, positive x and negative x, positive y and negative y, then we say the molecule is centrosymmetric and we give a G symbol, G-rayed symbol. If it is different, opposite sign, then it is called un-G-rayed or not centrosymmetric molecule. So look at this one. If I say these are the positive lobes, these are the negative lobes, and if you go from this end to this end, you have a positive end, this end to this end you have a negative end. So on both sides of the axis you don't have the same sign. Here you have positive sign, here you have negative sign. Here also in this direction also, in one direction you have positive sign, in another direction you have a negative sign. So this is un-G-rayed or not centrosymmetric and given a symbol U. But if you look at this overlap, here you have a positive sign, here you have a positive sign. So on both sides of the axis you have a positive sign. On both sides of the axis you have a negative sign. Okay. So it is a G-rayed molecular, it will give you a G-rayed molecular orbital or centrosymmetric molecule. If you look at this molecule, it does have a nodal plane also. Okay. So if you go from this to this, you have a positive sign here, you have a negative sign here. So it's un-G-rayed, its symbol will be U. Okay. And now you look at this one. This is positive, 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 positive. This is negative, negative. So this will be, symbol will be G. So that's another designation, that sigma G, sigma U, how do you write? That's labeling according to the molecular symmetry. Okay. Labeling of molecular orbital based on the symmetry. That's G-rayed and un-G-rayed. Okay. Now, what could be the possible combinations for sigma and pi bonding? So I said you 1s and 1s combination, 2s and 2s combination will not depend upon the x, y and z axis, because it's a spherically symmetrical orbital. But 2pz and 2pz will overlap to give you sigma orbital only when your molecular axis is z axis. So if we have taken molecular axis of z axis, so we say that at the bottom the lowest energy molecular orbitals which you get is, this one is a sigma 2s orbital, which is bonding molecular orbital and anti-bonding molecular orbital coming from these two overlap, 2s and 2s overlap. Then 2pz and 2pz will overlap to give you bonding and anti-bonding molecular orbital. And look at this molecule. Okay, if this is your center and you move from this end to this end, you move from this end to this end, you get the same sign. Okay, but here you don't get the same sign. Okay, you have a positive sign here, you have a negative sign here. This is the center. Okay, so it will be given a symbol U. It will be given a symbol G. Okay, so that I said you. This comes from the combination of 2px and 2px, or 2py, 2py. Both will give you the same condition, because one will be along the x-axis and another will be along the y-axis, but both will be perpendicular to the molecular axis. We are talking about diatomic molecules. Okay. So this kind of molecular orbitals you get. These are the molecular orbitals which you get for diatomic molecules, from for the diatomic molecules starting from H2 to neon 2. Okay. So these are the orbitals which you get. The 3s orbital we are not talking about. We are limiting ourselves to neon 2 molecules only. Okay. Now, the molecular orbital diagram normally is this one, that 1s and 1s combination gives you these two molecular orbitals, bonding and anti-bonding molecular orbitals, then 2s and 2s combinations, then 2p and 2p combination gives you bonding and anti-bonding. Normally, when you draw the molecular orbital diagram, you don't draw the molecular orbital formed from the core atomic orbitals. You only write the diagram of those orbitals which is in the valence shell. So valence shell 2s and 2p can combine, and that's why the dotted line is here, that we will not talk about this one. If you go beyond beryllium, carbon, oxygen, nitrogen, we will draw 2s and 2p only. Okay. So this is the simplest molecular orbital diagram which is drawn for the diatomic molecules. Okay. And if you look at the energy levels of these molecules, then for lithium 2, beryllium 2, boron 2 and carbon 2 and nitrogen 2, the diagram tells you that you have a 2s orbitals combinations. Okay. And you see what your pi molecular orbital is below this sigma. Okay. In case of oxygen and nitrogen, it is different. Okay. So this in case of, here the green circle tells you that the real shift is here, which takes place when you go from N2 to O2. So the diagram which I have drawn earlier is applicable for O2 and F2 only. Okay, below this, if you have, then what does happen? This goes here and this comes here at the bottom. So pi bond becomes at the bottom of this one, and this sigma shifts to this one because of the shielding effects and all those things. Okay. So this shift takes place in this case. The same shift is taking place. And this is a diagram drawn which is from P.W. Atkins, and you can see there that the shift, the color also tells you that all lithium 2, beryllium 2, boron 2, carbon 2, nitrogen 2 has the similar energy level, except that the energy of one of the orbitals, say 2 sigma g, goes on decreasing, and it decreases to the extent in O2 that it comes down. Okay. And in O2 you have 2 unpaired electrons, so you know that the paramagnetic properties of O2 is explained by molecular orbital theory. This is very common problem which is taught at the +2 level and undergraduate level, that the explanation for the paramagnetic properties of oxygen molecule, O2 molecule, comes from the molecular orbital theory. So for O2 and F2, the diagram remains same, but for rest of the thing, the one of the pi orbital comes below the sigma 2s orbitals. Okay. So this we have seen. Now this is a clear-cut distinction, that if you have N2 here, this is for N2, and this is O2. Okay. So you look at this part and this part, the sigma molecules, and then pi, and here you have first pi and then sigma. Okay, so this shift takes place. Pardon. Okay, sorry, this is not this I wrongly drawn. This goes where, and these come at the bottom. Okay, so this was the thing. Okay, O2 and F2. So this diagram clearly you can differentiate between N2 and O2 molecular orbital diagram. Okay, fine. Up to diatomic molecules, up to oxygen and fluorine, we can draw the molecular orbital diagram, we can draw the energy level diagram, we can draw the molecular orbital shape, and everything you can do. Okay. What about the triatomic molecules, say BeH2 molecules? Now, in case of BeH2 molecules, you have 2 hydrogen atoms, so 2 hydrogen atoms will contribute 1s orbitals, and in case of beryllium, you have S orbital also and p orbital also. So two different kinds of combination could take place. And again, if it's a diatomic molecule, it could be on one axis, and we suppose it to be z axis. So what we say that hydrogen of 1s and hydrogen of 1s, two orbitals of the 1s orbital, and one of the beryllium s orbital will combine to give you one bonding molecular weight and one anti-bonding molecular weight. Same way, beryllium pz and hydrogen 1s will combine to give you another bonding and anti-bonding molecular weight. And if you px and py will not combine, will remain as non-bonding with a zero overlap, because the next is what if you draw a px orbital, it will be px orbital, and if you draw s orbital of hydrogen atom, it will like this one. So a combination of these two is not feasible, and this there will remain as non-bonding molecule with zero overlap. Okay, molecular axis we take as z axis. So if you look at the energy level diagram, the energy level diagram is like this one. Okay, BeS2 molecule. Now, in case of 1s and 1s hydrogen atom will contribute 1 electron, and beryllium 2 electron will total will become 4 electrons. So all the 4 electrons will remain in the sigma bonding molecular orbitals. Okay, and this will give you BeH2 molecules. We can go ahead and we can talk about H2O molecule, a triatomic molecule, and other molecules also in the similar way. I will not talk about those molecules, but we will certainly talk about the molecules larger than that, that's conjugated molecules, in case of an extension to the molecular orbital theory with a drastic approximation done by Huckel in HMO, Huckel molecular orbital theory, that we will talk about in details. Okay. So I thought after doing H2 plus molecule ion, I should talk about some diatomic molecules. It's a quick revision of what you have already done. I did not talk about much about the quantum mechanics here. The qualitative picture which you have already done, I have just revised it for your memory. And now the application of quantum mechanics to the organic molecules we will talk about in HMO with some drastic approximations, that's called Huckel molecular orbital approximations. Okay. In the next module, in the next to next module or some module, we will talk about those things. Okay, thank you.